We saw when we were doing integrals in 2 dimensions, so regions in R2, that a lot of different regions we'd be interested in weren't very amenable to using rectangular coordinates to set up our double integrals. What we ended up doing was recalling polar coordinates and seeing how we could use polar coordinates to do integration. Well, now that we're moving to regions in 3 space, we're going to introduce 2 new coordinate systems that are quite useful for working in 3 space, known as cylindrical and spherical coordinates. So let's just start with a recollection of our rectangular and polar coordinates. So we knew that we could represent any point in R2 by its x or y coordinates. That's what we've always been doing. But we also recall that we could use polar coordinates, where we took r as the distance from the origin, and theta is measured from the positive x-axis. And so our polar coordinates were given by r and theta. And then we had these nice relations here where the x value is given by r cosine theta, the y value is r sine theta, and then we also had the r squared is x squared plus y squared, just using the Pythagorean theorem. So this could give us any point in the xy plane. So naturally, if I want something in 3 space, if I can tell you where it is in the xy plane, to get where it is in 3 space, I just need to tell you the z value as well. And so that's what cylindrical coordinates are. We just say where is it in the 2 dimensions, so we just go r from the origin, positive, and then theta from the positive x-axis, and then we go up in the z direction to get the coordinates in 3 space. So our cylindrical coordinates would be r, comma theta, comma z, and those are the 3 things that tell us our point in 3 space. So let's look at some examples of some pictures here for what these things are useful for. So if we fix a value of r, so in this case we took r equals 2 in this picture over here, and we just let theta and z change, we're just going to get a cylinder here. So that means cylinders are going to be quite nice to work with because they're just given by a function being r equals some constant. So those are nice to work with in this coordinate system, which is one of the reasons we refer to them as cylindrical coordinates. We can also say, well, what happens? We know what happens when we fix the value of z. That's just a plane. We saw that with rectangular coordinates. But what happens when we fix the value of theta? Well, in this case, it's just a ray going out. So this is here is theta equals pi over 4. So it's not a plane that goes in both directions. We just go out from, you can see the origin is somewhere in here. And we just go out in the direction of theta equals pi over 4. And we have every value of r and every value of z. So this is just like a half plane that starts at the z-axis and goes out in the direction of theta. So that's also another thing that's nice to work with if we have cylindrical coordinates, because it's just given by a constant value of theta. So that's one coordinate system we're going to work with. It's pretty familiar to us, really, because we've already done polar coordinates. So all we're doing here is adding a z variable to it. And it works nice with cylinders. Now, the next coordinate system we're going to work with is going to work nicely with spheres and with cones, but it's a bit more complicated to describe. So in this case, to represent a point in 3 space, we're going to give a distance from the origin and 2 angles. So we go out a distance of rho, so that's the distance from the origin to the point, and then that would give me, basically if I look at all points, a distance of rho from the origin, that would give me a sphere. And then if I specify how far I go from the positive x-axis, that puts me in this plane here, and then phi here telling me how far to go down from the positive z-axis gives us then we only have one point left. It's a distance rho, an angle theta, and an angle phi. So theta is measured from the positive x-axis, phi is measured down from the positive z-axis. So theta goes between 0 and 2 pi, it can go all the way around, but phi only goes between 0 and pi. Because if I went further around, then I'd have 2 ways to represent a point over here, because I could either go all the way around, or I could take the theta and go all the way around. So phi only goes between 0 and pi. The other thing to keep in mind here that's a little tricky is a lot of times if you use spherical coordinates in physics, they will call this distance r and this distance here rho. So we have to be a little careful of that. And they also often interchange theta, and phi. But since we're working in the calculus class here, we're going to stick with what is common in calculus textbooks. So we're going to keep our theta and our polar coordinates as r and theta, and then we're adding phi and rho in terms of spherical coordinates. Okay, so as we said, theta is the same angle as in polar coordinates, but phi is measuring down from the positive z-axis. And here, just like I said, rho is positive because it's measuring distance from, or it's non-negative because it's measuring distance from the origin. Theta goes between 0 and 2 pi, and phi goes between 0 and pi. And so just like we did with our cylindrical coordinates, let's see what kind of graphs do we get if we fix our various spherical coordinates here. So the first one I already mentioned is if we fix the value of rho, that's saying all of the points that are a fixed distance from the origin. So that's exactly how we define a sphere. So here's pictured when rho is equal to 2. So all the points here on blue are a distance of 2 from the origin. Now if we fix the value of phi, we're going to get a cone, because what we're doing is we have like the z-axis coming up, and we're fixing all of the points that are phi equals pi over 4 down. So you think of taking your z-axis going up and down, going to making like a line here at the pi over 4, and then rotating that line all the way around. And that would give us all of our points for phi equals pi over 4. So what we do here is if we fix phi, we're getting a cone here. So we saw spheres if we fix rho, now cones if we fix phi. So that means spheres and cones are going to be quite nice to work with in spherical coordinates. So we want to be able to move between our different coordinate systems for them to be useful. So we already saw this with polar coordinates, and since we're using z equals z when we go to cylindrical coordinates, we have the same conversion going between cylindrical and rectangular coordinate. Okay, so now the spherical coordinates. This is where it gets tricky. These are a little bit harder to relate here. Now, one that we can think of here, let's go ahead and label some of these things, is certainly if I go a distance rho out here, I can form this triangle with the r and the z. So rho squared would be r squared plus z squared, just using the Pythagorean theorem. Then I know r squared is x squared plus y squared. So rho squared is x squared plus y squared plus z squared. And now I can also figure out, well, what is to use to get these formulas here. I can say, well, if I look at my angle phi here, then r is the opposite of phi. So r is rho sine phi. So I'm going to take this r and replace it with rho sine phi in each of these. And this gives us our conversions for x and y to go to spherical coordinates. And finally, the z is the adjacent with my phi here. So it's going to be rho cosine phi. So you can memorize all of these if you like. I often just draw the picture because I will forget what they are. But if you can understand the geometry of the picture, especially if you remember the cylindrical coordinates, to get to the spherical, it's not so hard to just go ahead and draw a picture. So now if we remember when we were doing polar coordinates, what we needed to do to be able to do integrals with polar coordinates is we needed to find an area form that was given in terms of polar coordinates. So you're going to need to do the same thing here. We're going to need to give a volume form in terms of cylindrical and spherical coordinates. So that's our next goal. So if we recall for our polar coordinates, our delta A here is r delta theta. And the idea is this arc length here is r delta theta. And as long as delta r is very small, we can kind of think of this as a rectangle. So the area should be r delta theta delta r. And then it doesn't matter which order, so we can switch the order to delta r delta theta. So that's how we did the area form for polar coordinates. So now let's use this to do the volume form for cylindrical coordinates. So here, we still have this r delta theta here like we had before, and the delta r here. But now we want to go up a height of delta z. So if I want to say before this area here was approximately r delta theta delta r, then the volume of this box should be approximately the area here times delta z. So my delta v here, the little change in volume, should be r, and then r delta theta, delta r, delta z, and then of course we can change the order of those. Most times when we're doing triple integrals, we're going to want to go dz, dr, d theta, so that's why we write it in that order. But of course you can do these in any order you like. So our dv, our volume form, is r dz, dr, d theta. So when we do an integral in three coordinates and we want to use cylindrical coordinates, we always have to have r dz, dr, d theta. Just like for polar coordinates in two spaces, we always had to have r dr, d theta. So the next one is to do the volume form in spherical coordinates. And again, this is a little bit trickier to do. So let's look at a picture here. So what we can see here is we want to find the volume of this little box here. So this angle here, if I have a little delta phi, then I get a little rho delta phi to go for this part here. And then this side here, I can project this down, and this is an r delta theta in the x y plane. But I know that r is rho sine phi, so I can write this side here, this length here is about rho sine phi d theta, just replacing the r with the rho sine phi. And then the change in this direction is a delta rho. So I get rho delta phi times rho sine phi delta theta. So that gives me a rho squared sine phi, delta theta, delta phi, and then I have a delta rho here as well. And so taking in the limit, this gives me dv is rho squared sine phi, d rho, d phi, d theta, d phi. And so when we do an integral with spherical coordinates, our dv is always going to be rho squared sine phi, d rho, d theta, d phi. And so rather than just introducing an extra r like we had to do with polar or cylindrical coordinates, we need a rho squared sine phi every time we integrate. So it's easy to forget that, so make sure you don't forget we need to add that in when we do integrals. So now that we know the basics of this, we'll in class do a bunch of examples of how to set these integrals up and evaluate them with both cylindrical and spherical coordinates.